Hello, hello. My name is Abigail Asantua Tichi, and I'm a member of Group 5. I'm here to talk about um, inputs, outputs, organization in architecture. So, when we say inputs, outputs, organization, it refers to the way in which inputs system manage communication between the CPU memory and the external device. It is crucially the traffic control system that deals with data flow between internal computer components and our outside world. So this simply means that input output organization is how a computer takes in information from the outside, like from a keyboard, understands it, and then gives you something back, like showing it to you on the screen or something. So, why does input output organization matter? The CPU works at extremely high speed. That is it. That is in gigahertz, while input output devices are way slower. When there is no proper organization, the fast CPU will The fast CPU would constantly wait for slow devices, making a massive performance bottleneck. Good input-output organization ensures data transfer while keeping the CPU productive. So in summary of this, the input-output organization matters because it keeps the computer connected, fast and working properly with all the devices you use. And this is the end of my presentation. Thank you.
Alright, so for this video, I'm going to be continuing with the slides, and these are basic input and output system components. Yeah, so basically what the computer is to input and output information or data. So we have input devices. These are mouse, keyboard, microphone, camera, basic. Output devices, monitors, speakers, printers. We also have storage devices such as hard drives, SSD, USB drives, and communication devices like network card and Bluetooth adapters. And these make it easier for you to be able to input your data and also output them. We also have um, controllers, input output controllers, like specialized mini computers that oversee specific devices or device groups. So it's like you have smaller types of computers that they control specific devices. They are also some kind type of input output device. We also have input and output buses, and they are lines that transmit data and addresses and control signals between system components. Yeah, so the buses, they basically take um, addresses and information from one place to another in the computer system. Yeah, so basically that's it. I'll let my colleague continue with the next slide. Thank you.
My name is Michael Ampeduni Akonde. I'll be presenting on slide 7 and slide 8. So slide 7 begins with input and output communication methods. Now one, program input and output. It's called polling. And this is how it works. The CPU handles input and output tasks directly by repeatedly checking device status in a loop. And the process it follows is CPU issues a command to the device and it continuously monitors the device until it's ready. Then once ready, the CPU transfers the data. Finally, the CPU moves on to its next operations. So this is basically like The CPU issue the command to the computer, then it will continuously monitor the the device action. So even before and after giving the command, it monitors the device. Then once it's ready, it just transfer the device. Then finally the CPU moves on to its next operation. So we will move on to slide 8. So now in slide 8, it's still on the input and output communication methods. So the second one is interrupt driven input and output. How it works. Devices send signals to the CPU when they need attention, allowing CPU to work on other tasks for the meantime. And the root meanwhile, maybe you understand. So the process is follows. CPU begins input and output operations. CPU continues with other work or programs. Device sends interrupt signal when ready. So it's like when the CPU is doing other things and maybe at that moment another thing needs the CPU, that the device will send an interrupt signal like blocking the CPU from moving to the other task before coming to the main task they have to do. So it's like it blocks it from going to the other side before doing the main thing. Then CPU pauses current tasks and handles input and output. So that's what I just explained. It's like it pauses what it was doing first, then to come back to what it has to do before going back to the previous task. So that's the last point. CPU returns to the previous task. Like maybe you have to go to the market today, but before going to the market, you were doing something. So but but at that moment the market also needs your attention. So the market is like the market will send a signal to your brain, or your brain will send a signal to your body that okay, I have to go to the market. So you then go to the market after you are back, you come and do what you are doing before you planned on going to the market. So that's how everything works. So my colleague will continue with slide 9 and 10.
I'm Ajinai Solomon, and I'll be taking over from slide 9 to slide 10. And I'll be continuing with the input and output communication methods. The third one, which is the direct memory access. And this is how it works. Special DMA controllers handles data transfers between devices and memory without the central processing unit involvement. So the DMA don't need the processor for the transfer between devices and the memory. And the processes, this is how the processes are. The first one is the central processing unit provides initial instruction, which are source, destination, and size. The second one, control of the bus is handed over to the DMA unit. Thirdly, data flows directly between memory and the device. So the processor is not needed for data to flow between the memory and the device. The DMA handles all. And last but one, once finished, the DMA alerts the central processing unit with an interrupt. So the DMA will send an interrupt to the processor that is finished. Then the last one, the processor runs as normal. It continues as normal, as if like normal. And then we move on to the slide 10, which is the input and output interface types. And with that, we have two, which is the serial interface and the parallel interface. And with the parallel interface, it transfers several bits or bytes at the same time. And secondly, it is optimized for short distance communication. And thirdly, it requires more wiring and making it costlier. Like it makes it more expensive because it requires more wiring. And with the second one, the examples include the legacy printer ports and the internal port buses, internal system buses. And with the serial interface, it sends data 1 bit at a time through a single wire. It's also better suited for long distance communication. And the common examples are the USB, Ethernet, and SATA. Then the last one, more affordable and dependable across distance. So with the serial, it's more affordable and it's more dependable across a distance. Thank you.
So I'll be taking slides 11 and 12. So with the slides 11, we have the modern input and output trend. For the first point, we have the high-speed interference. So with this point, technologies like the PCLE, USB 3.0 or 4.0, and then the Thunderbolt deliver rapid data transfer between components. So this point is basically trying to tell us that devices like the PCLE USB 3.0 help the computer system to transfer data quickly between components like the storage, the graphics, or the memory. The graphics and the memory. With the virtualization output device enables multiple operating systems to share the same physical hardware, increasing efficiency and flexibility. So let's look at one physical input and output device like the printer. So the printer can be shared with many computer systems, making the system more flexible and efficient. And with the next point, we have the network attached input and output. So with this point, let's look at a device like the hard drives, which can be used over an internet, the which can be used over an internet, which is useful for cloud storage. So with the point 12, with the slide 12, we have the input and output system design challenges. So with the first point, we have the speed matching. So the speed matching addresses the challenges of synchronizing fast CPU with slow input and output device. So there are some input and output devices which are very slow, and to avoid delaying, we use the buffer and the cache, which stores data temporarily, and with the multiple processors which help the system to run smoothly. We have the error handling. The error handling focuses on detecting and removing from transmission faults. It uses techniques like the checksums and error correction codes to help maintain the data integrity. So with this point, we know that some data transfer can be a bit messed up, and this system helps detect them, and it also uses the checksums and error correction codes to help correct these errors. With the last point, we have the security, which shows system from malicious input and output device and implements access control to ensure only authorized communication with the input and output sources. So with this system, the system is being protected from harmful input and output device, and it uses the access control to ensure only authorized communication with the input and output sources. So I'll leave the next slide.
I'm Enoch from Group 5, and I'll be summarizing all what my friend said. So, the efficiency of IO organization is critical to the overall performance of a computer system. Strategic organization of IOs is necessary to maintain harmony, as CPUs and IO devices often operate at different speed. Modern technologies such as DMAs, interrupt and caching are employed this to bridge this speed gap and improve system responsiveness. These tools are critical for ensuring a smooth data flow, reducing delays, and optimizing overall performance. The slides emphasizes that a deep understanding and proper application of IO strategy are not merely technical details, but a fundamental requirement for building a powerful and responsive systems. Thank you.